In 1865, the world of military intelligence didn't exist. There were no satellites, no radar, no encrypted radio bursts. There was only math. A Scottish physicist named James Clerk Maxwell published a set of equations that did something impossible. They unified electricity, magnetism, and light into one single force. But at first glance, these were just four separate laws of nature. But Maxwell saw a two-way street. He realized that a changing electric field creates a magnetic one, and that magnetic field, in turn, creates an electric one. They were leapfrogging through the void, begetting one another in a cosmic relay race. He had found the mechanism for a wave that could travel without a wire. Maxwell plugged the known constants of nature into his math and found that these waves moved at exactly 186,000 miles per second. This wasn't a random number. It was the speed of light. In that moment, he realized the truth. He wrote, "The velocity is so nearly that of light that we have strong reason to conclude that light itself is an electromagnetic disturbance." He had discovered the mathematical ghost, the displacement current, a wave that doesn't need air or water to move. It is self-sustaining, independent, and it would eventually allow us to catch a whisper from the other side of an ocean. This is the spark that changed the world.
So, here we are. What I'd like to tell you is about this mysterious ghost that is all around us. Kind of like Star Wars, only real. That's right. This isn't science fiction. This is science reality. And we're going to go into it, and we're going to come out knowing exactly how this works and just how it's used by the militaries of the world. And even your own devices that you use every day, that every entity in the universe, in the world, uses every day to communicate. And not just communicate, but there's also more. Let's do this. Before we do, we have to go over we have to learn some different words. So what are these words? What do they mean? Let's do that now. Alright. So, before we really go into it, we need to learn about what did Maxwell really accomplish? Like, where was Maxwell in all this? So, well, there were these four different equations, right? And he thought through how to combine them all and actually be able to think through how they are all unified together. And that was actually through this one equation. This is sometimes referred to as the Maxwell relation equation. How about that? So, with this Maxwell equation, anyway, what he did was fairly magnificent, honestly. He was a really smart dude. Kind of wish he was my dad. Anyway, so he basically combined these four equations into one unified theory. I mean, he was only working with math, so really it was more just a theory that he ever could do. He was a mathematician. Give him a break. And so what he combined, right, was these two numbers into one equation, and this unified it all. How about that? Kind of cool. So, let's take this step by step, because this is a lot. There's a lot of information right here, and we're going to go by it in spoonfuls, if you will. Spoonfuls of sugar. So, let's take this spoon by spoon. Anyway, let's do this. So if we were to think about kind of get into our mindset about what these two different ideas are that are being combined, right? We got to think about there's these two forces of the universe, okay? So there's this electrical force that has this kind of idea of a stretching. It kind of stretches on the universe. And then this other one is magnetic force, and it kind of snaps. It's a snapping kind of force. It kind of wants to pull things back together, or pull itself together, I should say. So you have the stretching and snapping going on all around us. Yeah, it's pretty wild when you think about it. Anyway, so going through it, right? Yeah, when you want to measure electrical permittivity, right? So you want to permit, it wants to continue going, it wants to stretch. It likes to stretch things really good. Yes. So you have this one thing, it's called a farad. That's our unit of measurement. Yes. So a farad, though, is like it's a way of measuring electrical capacitance. That's what it's all about. It's being able to measure what a material's ability to store electrical charges. That's what it's all about. That's what it does. We can use a farad and we can measure freaking electricity with it. How about that? That's pretty cool. Okay, let's keep going. Anyway, so 1 farad, that is like a water tower of storage, of electrical storage. That's pretty wild. That's a lot, if you think about it. So next thing down, right, is we have 1,000 microfarads. You gotta think about that, right? 1,000 microfarads. Already small, and we're making it even smaller. And then we're just putting 1,000 of them. What we get for that is 1,000 times 10 to the negative 6. Yeah. So that is a 5-gallon bucket of water. Boom. That's a lot. That's still a lot. I mean, I couldn't drink all of that, but that's a lot. The next is we have 1 microfarad. So if we took just one of those 1,000 microfarads, what do we get? We get a coffee cup of water. That's the equivalent of this electrical charge in a 1 microfarad. That's it. 1 coffee mug. Boom. So then we have 1 picofarad. That's even smaller, of course. It's like a single drop of water. What does it look like? Well, it looks like 10... Well, it's 10 to the negative 12. That's what we're looking at with how small and teeny tiny this is. That's unfathomable by me, anyway. Anyway, so we have this thing now. Now that we've gone through those, now we have this idea of what an epsilon naught is. How about that? An epsilon naught. Yes. Anyway, so an epsilon naught is like 9 drops of water. So that 1 picofarad, epsilon naught is like 9 of those. That is the number that we're trying to get to. Now we kind of step down in size to the point of where we can kind of get an idea of what this looks like. Because you can't see this, right? You can't see what a farad is. You can't just look at it and be like, oh, that's definitely a farad. You can't do that. So, what you do is we do this so you can get an idea of what a farad would look like if you could see it and be like, oh, that's a farad. Bam. Hot damn. Anyway, so an epsilon naught, right? Let's get down to dirty numbers. Epsilon naught is 8.85 times 10 to the negative 12. And that is an epsilon naught. Boom, baby. Boom, body, boom. That's a teeny tiny microscopic. I can't see that kind of number, okay? So now we have that teeny tiny number that I could never think of if I tried. Next one is Henry. Let's go over what a Henry is, okay? So a Henry is the permeability, or the ability for magnetic force, okay? So that's what we're looking at. 1 Henry is like that of a semi-truck in weight. Now when we say weight, it's just like with electricity. You can't see it, you can't I mean, you kind of feel when you put two magnets together, you kind of feel that kind of thing. There's a little bit of weight that you're pushing against. That's kind of what we're talking about. How about that? Anyway, so 1 Henry is like a semi-truck, of weight. Just to give the idea of like how heavy this would be if you put a weight to it. Yes. Okay. So then we have 1 millihenry, and that is, just as the name applies, it's very small. It's even smaller. Well, it's small. It's very, very small. So if we were to go from 1 Henry to 1 millihenry, you got to think about the size difference in that, right? So we're going from a Henry to millihenry, and so going from a semi-truck, a huge giant thing weighs a lot, to a bicycle. That's the weight of a millihenry. How about that? 1 millihenry. Bada bing, bada boom. That doesn't weigh as much. Then we have 1 microhenry. Bam. So we're going back to like 1 times 10 to the negative 6. Yes. That is like, putting it onto a size of scale, grain of rice, if you believe it or not. That's like really, I was going to say how you could throw a whole bunch of those, and that would be like, that's like the weight of a microhenry. A grain of rice, how about that? Then we get down to a 1 nanohenry. That's like a speck of dust. And this is 1 times 10 to the negative 9. Nano. That's kind of gives them what it implies is a nanohenry. Boom. So then, now that we have these kind of ideas in our mind, we can kind of think through, right, what is a mu naught? Oh, funny you should ask. Thank you for doing so. It's good. Good thing you're thinking like that. Okay. So, 1 mu naught. Because this is like the important number, right? This is like what our measurement, this is what Maxwell, so these numbers were already thought of, they're already known, they just were never applied in this way, in this manner. So, Maxwell's kind of genius. He's like, I'm going to put these goddamn numbers together. So he did. So we already knew about mu naught, right? And so that number ended up being 1.256 times 10 to the negative 6. Very, very teeny tiny. Same thing as epsilon naught. Very teeny tiny. Can't see it. Too bad. So sad. Just your lot in life. Don't get to see it. No one gets to. Okay? No one gets to see it. That's mu naught. Boom. So, what he did, right, what Maxwell did, is he put these two numbers together, right? That's what this equation up here is all about. Putting those two numbers together. He's like, I'm going to see what the hell happens when I put these two numbers together. Let's see what happens. Boom. So he did. But before we get into that, let's get into some more applicability. I like that, because then I know, like, what the hell it is that is even all about this. So I'm going to do that real quick. Right? So to kind of give more of an idea of, like, what Henrys are all about and what they mean, and how I can think about them in the future. Right? That's what it's all about. How do we think about these in the future? Bada boom, bada bing, dabba dabba dee. So, when it comes to these mu naught units, right? Thinking about them in a unit. Mu naught meters. Mu naught and just go with it. So 5G smartphone uses 1 over 125 mu naught units. So we're talking about this 1.256 times 10 to the negative 6 units. Mu naught units. And so when we say mu naught unit, it means that 1.256 times 10 to the negative 6 unit. That's how teeny tiny this is. Okay. Keep on tracking. As long as you are, we're tracking. Next is we have the Hertz experiment, which we're going to actually learn about later, funny enough. is 1 mu-naught unit. It took 1 entire mu-naught unit for Hertz to do his experiment. Yes. Then we have a CD player motor. These things that used to exist that people would listen to once, like probably like a handful of songs at one given time, because everyone was like, I really just cannot live without listening to this freaking song right now. So I'm going to listen to this on this freaking CD that I went to Walmart for and bought. That's what CDs used to be. There you go. 400 mu-naught units to be able to get that motor in that CD that you've probably never even seen before to actually spin the CD so you could listen to the, you get the idea. Then the next one is a washing machine. How about that? To get your freaking washing machine in your house that you probably have because you're really, really rich. It takes 200,000 mu-naught units to get that thing to spin. Boom. Then we have an elevator motor. Yes, to get that freaking thing up and down, it takes 2.8 million mu-naught units. This is the really, I'm hoping like you're, like the idea of like what the size of scale really looks like. Hoping that you're like, if not, put in the comments, let me know how, like, if you're able to grasp this, that'd be really awesome. Trying to get better at this, as we all are. Scrap magnet. 12 million mu-naught units. Like, I can't think of that. That's just insane and huge. Like, I mean, I can see what a scrap magnet looks like. I've seen them on TV and on movies before, but think about, like, how much weight it's able to, that really just means it's difficult. This is a difficult thing to really think about when you think about it. Then substation, 80 million mu-naught units. This is just like, what are we even doing anymore? That's to kind of give, I hope, a good idea on just like what these units of measure are like meant for. I mean, no. No one's ever going to be like, hey, like what's a mu-naught unit? And like, oh, well, funny enough, I just now know that. No, it's just to kind of give the idea of like what these numbers really look like when you put them in scale. That's it. You're welcome. So then we look at what it looked like when when Maxwell put these numbers into his equation. And what came out was pretty fascinating. So let's look at that now. Bam. So put 1 over C equals, so that's mu-naught times epsilon naught. So we're going to take those two numbers that we had before, even before Maxwell, we had those numbers. So let's put them in and see what happens. Ba-boom. 1.256 times 10 to the negative 6 times 8.85 times 10 to the negative 12. Alright, so we put those numbers in and we get so we times those, we get 11.151, and then we do the 10 times negative 6 times 10 to the negative 12, we get 10 to the negative 18. It's pretty simple math. I mean, it's okay. To be honest, okay, maybe it is a little bit, and maybe it's not. I am not here to judge you. If you get it, then cool. If not, like, just let me know, and we'll kind of work on that. Okay. So then we have mu-naught times epsilon naught, and then we have the 11.151 times 10 to the negative 18. So what that actually got us, right, is this number right here. Unfortunately, there's a problem with this. Can't do anything with it. It's actually pretty meaningless. I wouldn't know what that means. It's 11.151 or something. So you have to think about, okay, what was the mu naught and epsilon naught numbers. Like, what are their units of measure? Well, one's measuring electrical charge, one's measuring the magnetic. Unfortunately, they don't work. I mean, they're not compatible like that, but crazy enough, they actually do have variables within those that actually allow them to actually be put together, and we get a fascinating number out of it. How about that? That's pretty cool. So, what we get, right, is a farad. A farad meter is amp times seconds over volts. Boom. Then we have henries per meter, and so that is volts times seconds over amps. So, if you're following, and I hope you are, we kind of cool. It means that I'm doing something right. But anyway, that means that we have like terms. And I'm going to bring you in closer so you can see this. That's what you can see right here, right? So we actually have like numbers, or we have like variables. So we have amps over amps, and we're actually doing the time. So if you know algebra in any kind of way, I hope you do. That'd be really awesome, because algebra is kind of good. So we can then take these, cancel those out, and volts is the same thing because they're both on opposite sides of the divide line. So we cancel those out, and then all we're left with is two S's over a meter squared. So we're going to take those and put them over here. You can see that now we have second squared over meter squared. That's all well and good, right? That just puts it over here. So we now have 11.151 times 10 to the negative 18 second squared over meter squared under a square root. So we were going to get rid of that square root, so we're going to lose the second squared and meter squared. So then we have 3.339 times 10 to the negative 9 seconds per meter. Well, we don't want seconds per meter, we want to know meters per second. So in order to do that, we need to put 1 over 10 times, 1 over 3 times 339 times 10 to the negative 9. That then gets us meters per second. That's what we want. And the number that we get, as crazy and as fascinating and as weird as it was back then, as it is still to this day and to me, I mean, I don't know about you, it's pretty wild. If you don't know what the number is, you're going to learn about it now. 299 million meters per second. The speed of light. Is that pretty wild? I think it's pretty wild. That is pretty wild.
By the late 1870s, Maxwell's theories had hit a wall. While the math was perfect, it lacked physical proof. The world was waiting for a translator, someone who could turn abstract calculus into a physical reality. Heinrich Hertz wasn't interested in the philosophy of light. He wanted to build a trap for it. The engineering begins at the source. The charge starts from the battery, flowing into the induction coil. It builds up a massive electrical pressure, a voltage so high that the very air between these brass spheres begins to scream under the strain. When the voltage hits the breaking point, the air is ionized. It becomes a conductor for a split second. The circuit is closed not by a wire, but by the atmosphere itself. And in that violent moment of discharge, a mathematical ghost is born. An electromagnetic wave that tears across the room at 186,000 miles per second. To find this wave, Hertz didn't need a bigger telescope. He needed a faster shout. The physical size of his copper loop acted like a tuning fork. If the loop was perfectly tuned to the frequency of the pulse, the ghost would appear. He was punching the universe and waiting for the echo. Wait, did you see that? That tiny spark in the receiver is the physical proof of every equation Maxwell ever wrote. Proof that Master Maxwell was right. This is the birth
of LC resonance and the specific frequency of the universe. But here is the great irony of the science of military intelligence.
Professor, what is the
When his
significance
students
of this
asked
experiment?
what this breakthrough could actually be used for, Hertz was dismissive. He famously replied, "It's of no use whatsoever. This is just a laboratory experiment that proves Master Maxwell
Sir,
was right."
if I may inquire,
When they pressed him further,
is there any
asking if there
practical
was
utility
any
at
practical
all
utility
to
at all,
these phenomena you
he
describe?
simply shook his head. "I do not think that the wireless waves I have discovered will have any practical application. We have these mysterious electromagnetic waves that we cannot see with the naked eye, but they are there, and that is all."
So, we just heard about Hertz and what he did, which is pretty cool, if you think about it. I think about it a lot, and I think it's pretty amazing. Kind of a dude that I would like want to sit down and have a beer with and be like, wow, you're like really smart, dude. Man, if I could just like hang out with you more, like, that'd be pretty cool. And then we'd be like, what else could we do with this? That would have been pretty cool. But of course, years of separation and him being dead kind of put a damper in that dream. So, that's not gonna happen. That really sucks. Anyway, so how do you take Maxwell's theoretical wave, a mathematical prediction from 22 years earlier, and actually build one in a lab in 1887? That's a good question. That's a phenomenal question. How do you do that? Let's think about it. I don't know. But we're gonna figure it out. Here we go. So, you start with the question. How fast do I need to shake an electrical field to launch a wave I can detect across the room? Boom! To do this though, let's imagine a kid. And this kid A, is a big kid, and he's swinging on this very long and very loose chain, right? He's doing that, and so when he swings, he's swinging very, very slowly and making these big, big swings. So he's moving very slowly, but when he does, there's a lot of momentum in that swing, right? There we go. But then kid B, he's actually gonna be a lot smaller, and the chain that he's swinging from is a lot tighter. Well, so then that makes him swing a lot faster, because that chain doesn't have as much give and take. So, in electrical circuits, the inductance, measured in henries, is the weight. The weight. The semi-truck from earlier. Boom. You got a Henry. You're moving pretty slow. But when you do start moving, you are moving, and there's nothing stopping you. Good luck. Everyone around me, get out of the way. Get out of my way. Measured in henries is the weight, the semi-truck from earlier. It's the magnetic inertia. This magnetic inertia, it resists change. Doesn't like it. It does not like things changing. Probably just calls everything bastards all the time. You bastard, you bastard, you bastard. Then, oh, you really want to change? You really want to have things changing? I'll show you what happens when you fuck around and find out. You'll find out what happens when you want to change this much. Then you get bad things happening because you are screwing around with physics way too much. Then you have the capacitance, which is measured in farads. And it's the spring in this universal relationship. And this is the water tower. It stores the energy, your electrical energy, and releases it. So when you do that, and you have this magnetic inertia, you have this relationship between electrical energy and the magnetic inertia. You've just found the universal relationship. The relationship of the universe. And they are forced to get along for time and all eternity. For real. And so, I don't know, but maybe you can relate to this. I certainly have thought about it, but maybe you are in a relationship that can relate to this. But like some relationships, there's one that really likes to see things change and move, and maybe the other one doesn't like that change so much, and the problem, like there's the friction between the two that is constantly there, and there's no escape. See what I mean? Universal relationship. Not just you are in a relationship that maybe it's not the greatest, but it's okay. They're not the only one. So, moving forward. The frequency, how many times per second the electric and magnetic fields swap back and forth, is F equals 1 over 2 pi square root of L times C, which is L is inductance times C capacitance. So, just like with our whole metaphor, if you have these as really big numbers, the slower this oscillation is, whereas you have these as being small numbers, then you're going to have a faster oscillation. How about that? Then, so every wave, let's see, Hertz didn't just need a fast oscillation. He needed the frequency to be high for a very specific physical reason. And this is actually pretty key in his whole thing. Because yeah, he really did. Every wave has a wavelength. That, to me, that's like, to be honest, that sounds like a kind of an oxymoron. Yeah, duh. Every wave has a wavelength. You bastard, stop challenging my intelligence. I'm sorry. Like, I'm not trying to, but it's good to like put these in place so that we can kind of move. It builds trust. Just trust me in the comments. This stuff, there's a point to it. So don't judge me too harshly, please. Okay. So the physical distance between one peak and the next, right? And please don't judge me on this either, because I mean this is just about like trying to get the idea across. Okay, everybody, it's cool. I promise you, there's so much good content that's going to be coming along, and it will be phenomenal. Just go with it and don't judge too harshly on this minor stuff. This is so minor in comparison to where this is going. Trust me, this is not the stuff to get nitpicky about. But this is typically how a wavelength is measured, right? Peak to peak. This is how we measure a wavelength. It's pretty cool. So in order to know what this wavelength is, right? What this wavelength is, we take the speed of light over the frequency. So we can take this right here, right? Put that under this, and then we get our wavelength. That's pretty awesome, right? Like we are getting like some really essential information from these two equations right here. Like, and it's building up. It's pretty cool. So yeah, Hertz was in his lab, and he had a problem, right? His lab was maybe like 15 meters across. Like, so if you want to measure something that's in such a small area, you need to be kind of cognizant about how big of a wavelength are you wanting to have to measure this. I mean, you got to think, right? Like, this was back in the day. He didn't have the internet. He didn't have any type of stuff. He had books on math, and that was it. Like, he didn't have Google or anything. Like, he had to like theorize and like kind of go through the numbers to be able to like figure out, maybe this will work, maybe this will work, maybe this will work. That was his process, basically. Like, just putting it all together and hoping like something cool comes out of it. And like, it's not like just pseudoscience. This was real, because this is like, you actually got something real cool out of it. So, what happens if, let's see, and Hertz had a problem. Let's see, so to see those standing wave patterns, to find those nodes and peaks, the wave had to be short enough to fit inside his lab. That was pretty big. So he needed to have this in a short enough distance that he would be able to detect it within his own room. It's like, let's see, if we plug 1 Henry, right? 1 Henry into this formula, right? Into this formula, check this out, right? I'm gonna bring it in. So we can see from here, right, and from his final paper, from Hertz's final paper that he submitted, right? So he conducted his equation, or his experiment that he submitted with using 50 megahertz. And we're going to kind of go over why he did 50 megahertz. But he actually did mess around with like a lot to try to like just see like what was possible, what was this new phenomena that he had discovered. And so he messed with a lot of this, all the different variables, to really like try to understand what this whole thing was, and it was pretty cool. So yeah, like that was his whole thing. Like, I'm gonna do all these kind of things to try to figure out what is this. It seems kind of cool, and it seems like this is legit. I mean, like it's very, very real. Like it exists. Like, what is this? They were still at that point of like just trying to prove to the whole, not just to himself, right, but to the whole scientific community, this thing exists and it's real, and Maxwell is right. I mean, people didn't like it. You gotta think about it. Like, you are like fundamentally proving the science of the universe. And when other people are like trying to make their own theories and they have their own ideas on how it all works, and you come out and saying like, actually, this is what I discovered, this is how I'm proving it, and this is why I'm right, you're gonna have a lot of pushback. No one in the scientific, like, I mean, you gotta think, people are spending their entire careers in these fields, and here it is, this 36-year-old dude coming along like, hey, check this out, I just figured it all out, and look what I proved. Boom. Ooh, you're gonna have some rivals, I'll put it that way. So, yes he did. That indubitably he did. But that's not the point of this. The point of this video is about the kind of cool stuff he did. So let's get back to it. Let's get back to why he used 50 megahertz. Let's legitimately look at that now. Okay. So, let's bring you in again and we'll kind of go over this. So if we take that 50 megahertz right there, right here, and then we plug that into our formula up here again. So there we take our 300 million, right, meters per second, and we put it over our frequency of 50 megahertz. Let's see if I can get that better. So we got our formula. Then we have speed of light, 300 million meters per second over 50 million megahertz. And so, and that's what, and since these megahertz is measured in per second, cycles per second, that's important. Is frequency is cycles per second. That's important, yeah, especially for this, because this is where things kind of get cool. Okay, it gets kind of really cool when you know like what's going on. Bam, it's pretty cool. So what happens here is, right, so we have our 300 million meters per second and our 50 million cycles per second. Now watch what happens. Now watch what happens. Bam. So what we do then is we're going to get rid of all these freaking zeros. All right here, because we can get rid of those. They all match. So we can get rid of them. Bam. So then what we have is 30 over 5. Bam. Which gets us 6 meters. 6 meters. He was able to use, that was the big reason why he used 50 megahertz, so that he would have this wavelength. Every 6 meters there would be a wave, a peak, another peak. That was the whole thing. So he was then able to then put the receiver 6 meters away and detect. And he was able to detect the wave. That's pretty cool. So now to kind of give kind of an idea about like what this is, more practical application. There we go. So now that we kind of gone over that a little bit, I hope that was kind of cool. It was kind of cool to me. It is pretty cool stuff when you start to like understand the science behind it all. It's kind of cool. So let's do this more with a practical application. A kitchen microwave that you probably have in your kitchen because cooking is hard. Let's be honest. Who really likes? Okay, so there's food aficionados. Boom. Fist bump to you for liking to cook. I'm not one of those. I don't think I ever will be. I hate to cook food. It's kind of dumb. I don't like cooking food. I like eating food. Don't like cooking it because I want to just eat the food while it's being made. Let's be honest. I don't know how many other people like are just watching food networks and they're like, okay, I'm done making this stuff. I'm just gonna eat it. I have those moments a lot. But anyway, that's not the point of this video. This video is about the kitchen microwave now. So we're going to go over that a little bit, and then one other thing, and then we're going to keep going. How about that? Here we go. So kitchen microwave, right? Typical kitchen microwaves operate at 2.45 gigahertz. What does that really look like? That's pretty cool, right? Like if we kind of like got that down and measured it. Let's see. So let's do the same thing we just did with Hertz. Experiment. Bam. So, kitchen microwave, 2.45 gigahertz. We translate that to 2,450,000,000 hertz. Okay, and then just the same thing with this formula. We'll put it in and see what pops out. We can get our wavelength. So then we have our 300 million meters per second over our 2,450,000,000, right? We cancel out all those zeros, right? Then we have just 30 over 245. I kind of missed this before, but it's important that we kind of cover, because we have second over here and second right here, those cancel out. So then we're just left with meters. That's how we get that. That's how we just get a measurement. Now we know we're just dealing with just meters. I think that is like one of the coolest things in math ever possible, is that things like that can cancel out because of that. And then we get our actual measurement. And so when it comes to kitchen microwave, we go through this, we get 30 over 245, that becomes 0.122 meters. When you translate that to what it would look like, it would be 12.2 centimeters. And if you're like me in America, that doesn't make sense because I'm not metric, I'm American. We get 4.8 inches. So 4.8 inches, that is the wavelength of a microwave. And I think that's kind of cool. Yes. Bam. 4.8 inches is what your typical microwave that you have in your house, the wavelengths are. I think it's pretty cool. 4.8 inches. So the last point, though, that I was wanting to get to, and we're going to keep going, is Oliver Lodge. So Oliver Lodge is kind of an interesting story, because he was kind of a bit of a rival to Hertz, because he was actually working on the very same problem Hertz was. We almost could have called them Lodges instead of Hertzes. How about that? That's pretty cool, kind of interesting, and just shows you what happens when you are beaten to the punch and someone else's name is plastered everywhere. You are forgotten. Ouch. And that hurts to think about. We call them Hertzes, not Lodges. Boom. So, he measured the wavelength of his wave, the physical distance between wave peaks, by moving a reflector and finding the standing wave pattern. And he already knew the frequency of his circuit by doing this right here. V equals F times the wavelength. Frequency times wavelength gets you that. Maxwell said that the wave should go this fast. Hertz measured it. It did go that fast. Case closed. Now, Hertz proved the wave exists, but his receiver had a problem. To see that second spark, you had to squint at the tiny gap in a dark room. And let's be honest, that's not practical. Like, it's a tiny, tiny spark. And like, it's kind of cool, but unless you are really, really close to this tiny, tiny spark, you're not, like, what do you want? Like, a high five? Anyway, so the cohere, a glass tube full of loose metal filings. Normally the filings are scattered and no current flows, but when an electromagnetic wave hits the tube, the wave's energy makes the filings clump up, they cohere, and suddenly current flows through. And Oliver Lodge, he did something Hertz never did. He actually sent a message. Like, he was the first person to ever send a message wirelessly. And he did it 60 yards. Like, is that crazy or what? He sent the letter A in Morse code. 60 yards. He sent the letter A. A, he's the original Fonz. Bam. A. So letter A was one dash. Just electromagnetic waves and a tube of metal shavings. Bada bing, bada boom. And now, a 20-year-old Italian named Guillermo Marconi is reading about this in a magazine, and he has a very dangerous idea. What if 60 yards isn't far enough? What if it's not?
The world disagreed. Within a decade, a young inventor named Guglielmo Marconi turned Hertz's useless spark into a global industry. He wasn't just catching echoes, he was building a megaphone for the world. Marconi's genius wasn't in the spark itself, but in how he tethered it. He added an antenna, his aerial, to reach into the sky, and a ground connection to use the Earth as a massive conductive plate. This wasn't a laboratory whisper anymore. By using the ground and the air as part of the circuit, he had increased the range from a few meters to thousands of miles. At the receiving end, Marconi used a tiny glass tube filled with silver filings, the coherer. When the invisible wave struck, the filings would cohere, completing a circuit that signaled a relay to strike a bell. It was the first time a whisper of energy could cross the Atlantic. He built a global monopoly on the airwaves. If you were a ship at sea, you didn't just buy a radio. You leased a Marconi room and hired Marconi men. These operators didn't report to the ship's captain. They reported to Marconi. By 1912, every major Navy and luxury liner was obsessed with this tech. Radio had become the ultimate tool for moving information. But while they were obsessed with the power of the shout, they were completely blind to the potential of the echo. And that oversight began 8 years earlier, in a harbor filled with fog. While Marconi was building empires of sound, Christian Hülsmeyer was looking for the echo. In 1904, he built the telemobiloscope, the world's first practical radar system. But he wasn't just shouting into the air. He was trying to aim the shout. Hülsmeyer realized that if he placed his spark gap at the focus of a curved metal dish, he could create a directional beam. Much like a searchlight concentrates light, the telemobiloscope concentrated radio energy. He wasn't broadcasting to the whole world. He was pointing at a specific target. This is the physics of reflection. When the radio wave hits a metal object like a ship, it scatters. A tiny fraction of that energy, a ghostly echo, travels all the way back to the source. Hülsmeyer proved he could see ships up to 3 miles away in total fog. But he hit a scientific wall. He could tell you where a ship was by pointing his machine, but he couldn't tell you how far it was. He lacked the clocks to time a wave moving at 300 million meters per second. To the navies of 1904, it was an impressive toy, but a tactical dead end. The world was too obsessed with Marconi's shout to listen to Hülsmeyer's echo, and that neglect was about to become very expensive.
Welcome back. I'm your host, Keith Sinks. This is the spark that changed the world. And so far, we've covered various different parts of this new evolving understanding of the EM wave and how we were learning to harness it. There was Marconi, and we were learning how his pulse that he used. He wanted to get every ship on the horizon to
be able to hear his shout. Whereas Hülsmeyer, he actually approached it from a different kind of way. He wanted to direct that energy in a focused direction. This would allow not so much to be able to direct it for communications, but for something much more intelligent, in my opinion. He wanted to get this thing that's called echo. Yes, he wanted to know something was somewhere, it was located somewhere at a distance. That was his thought in how to use this phenomena, was to be able to detect something at a distance. That to me is pretty cool. A pretty cool kind of thing in my book. That's what I'll call it. Cool thing in my book. Yes. So, but to do this, what was really necessary to actually accomplish? That's a good question. I'm glad you asked. Thank you for asking. Man, you're smart. Good job. Anyway, so what was necessary? Well, you needed energy, and a lot of it. That also, energy required was kind of a downer for those that would be using it. That was just part of the problem. Let's look at this, shall we? So, the problem was, right, when it came to the amount of energy required would be going out, and so think about this, right? Let's think about this. You use a flashlight, right, and you shine it at a wall from 1 foot away, right? You can see a nice, clean, crisp, and clear line, circle, right? It's pretty good. Then you move that flashlight 10 feet away, and now that same circle is much wider, and the light dissipates much further out. This is the same problem when it came to Hülsmeyer's echo. The more distant the object, the smaller the return would ever be coming back. This is the problem, because the more you had to be able to do this, the more power you had to give it to be able to hear anything in return. That is a problem, if you think about it. And now we can kind of look into how much of a problem this really was. Let's look at it. So, there's this thing called it was this thing called the inverse square law. So as a pulse travels out in 3D space, it's losing power. It's losing double its power as it travels outwards, right? So that was part of the problem. Then, as it's traveling out, right, and you're wanting to detect this ship right here, right? How this works, right, is that it bounces off, and so we kind of zoom in on this piece of metal that's on this ship, and we can see like all these free electrons. This is how the science of the echo really worked, right? So this wave would actually bounce off these free electrons in this metal, and then it would bounce off this free electron, and it would emit a new wave, an entirely new wave, 180 degrees from where it received it, and send it back out. So that was already an inverse square law going to it. So now, going back to say 180 degrees, you have to factor in that inverse square law again. This then becomes the inverse fourth power law. So now, instead of losing double, it's actually losing 16 times the amount of power you've just now lost. This effectively was the problem that the German Navy at the time, they recognized as a no-go Joe kind of problem. We are not going to send this kind of amount of energy out to lose that much power just to see if something is there, and this doesn't work very well. That was kind of part of the problem. Now the other second part of the problem we're actually going to get into. Because as the second part of the problem was a clock. We did not have at the time, the technology was not there to know the timing required to get the range. It could detect bearing, right? That was the whole idea of this. Was you could get bearing. You could not get range. And that was a problem. Could not get range because we did not have the clock for it. So he had actually a workaround for that. And it was kind of a trigonometric hack to be able to get distance. And I mean, don't get me wrong, the math involved is still pretty interesting. We're going to kind of learn a little bit about that. So let's do it. Okay. So we have this equation right here. Distance equals h over the tangent of theta. Now this is important, okay? So height, h is height. So we have that over here, right? So we have height. So if we know what our height is, which for us, we would be placing the height of it on a mast of the ship, right? So we'd have the bottom of the ship right here, and then so we're placing the antenna way up high, because the higher up you are, the further distance you can see. That's pretty cool. So this is how it would work, right? You have a 90-degree angle, and you have this, and you can direct your device at whatever specific angle. Oh my God, I'm sorry. Let me see if I can do this. There we go. So, here we go. Yes. So, we have our height, right? So if we know the height of the mast, and then we can direct this would be Hülsmeyer's telemobiloscope. We can, if we know what angle we are pointing this, right? Whatever angle we're pointing it, whether downwards or more upwards, we know the angle, right? Those are numbers that we need to have to be able to get our distance. So what we need to know is theta, right? And then tangent is opposite over adjacent. So our opposite, right, is our known constant of the height of the mast. Then we just need to know the angle of which this is pointed. Then we can get our distance. And that was the geometry, or the trigonometry, of knowing how to get the distance to this ship over here. And that to me is pretty cool, because I mean, as we all know, right, a triangle is nothing more than 180 degrees. So all you have to do is just do 180 minus 90 for the one angle. That already eliminates half the problem right there. Then you just eliminate this degree right here, and now you can get your distance. That's pretty cool. So the only other problem that was really faced, right, was, of course, they didn't have they didn't have calculators that did trig functions like they do today. That wasn't like a thing. Yeah, but they had these things called trigonometric tables that basically gave all the numbers. Like the mathematicians published these books so that they were already known, so you didn't need a calculator. You just look through this freaking book to get numbers you were looking for. That would not be fun. I would not want to look through a book that big. That just sounds terrible. So But that's what they had at the time, is a book. They didn't have a calculator, they had books. But for Hülsmeyer, he actually created this thing called a slide rule, and so it actually would give the height, like the height of these masts were already known, so he would just put those as the constant, and then he would just give the angles for each of the angles to give distance. So all they had to do was punch in those numbers, and the distance would come out. That was pretty easy. Here's where the problem really fell then with this, because even though that's all well and good, right? Comes back to that whole thing that happens to ships out at sea, is they're doing this a lot. I don't remember the correct terms, but they're pitch and yaw and just rocking back and forth so much in the sea that you're trying to angle this and try to figure out what it is. It would be problematic, especially as the higher you go up, the more of everything is rocking, it just becomes even more problematic. So for him, that was a hard no from the Navy because of that. Because you're really fighting a lot of elements that you have no control over. So that's kind of about Hülsmeyer and why the military said no. But as we'll learn next, is the problems with no governance on this technology at all, and the consequences that arise when there is no governing body. So here we go.
In 1912, the mathematical ghost was in its infancy. Radio was a rudimentary tool, a brutal spark gap that didn't just whisper through the air, it shouted across the spectrum at once. Its primary roar sat between 100 kilohertz and 2 megahertz, but the electrical chaos sprayed interference into every band above it. In technical terms, it was a broadband nightmare. Think of modern radio like a laser pointer. Precise, narrow, and easy to ignore if you're not looking at it. But the Titanic's transmitter was a lightning bolt in a bottle. Because it wasn't tuned, it released all its energy in one massive, undamped crash. It didn't broadcast on a channel, it broadcasted on every channel. This is why the Spectrum Authority had to exist. Because there was no standard for how to listen, the SS Californian was only 10 miles away, but its operator had gone to bed. There was no law requiring 24-hour watches, just the early adoption of a tool we hadn't yet learned to master. The silence was born from a collision of signals. In the U.S. Senate inquiry that followed, the world learned a chilling truth. The system didn't fail because people were lazy. It failed because the technology was too primitive and the rules were non-existent. We were adopting a technology before we had a protocol. Cyril Evans, the operator of the Californian, tried to warn the Titanic about the ice field. But because they were so close, and because these early transmitters were so broad and unpolished, his signal was deafeningly loud in the Titanic operator's headphones. It was like a neighbor shouting through a megaphone into your ear. Jack Phillips snapped back. "Shut up! Shut up! I am busy. I am working Cape Race."
Shut!
To a modern ear, this sounds like an argument. But to military intelligence, this was a preview of jamming. Evans followed the only code they had, the unwritten law of politeness. He kept out of the way so his neighbor could finish his work. At 11:35 p.m., he took his headphones off and went to sleep. 10 minutes later, the Titanic struck the iceberg. Once word of the disaster leaked, the problem flipped from silence to total chaos. Thousands of amateur enthusiasts flooded the airwaves. Because their devices were so rudimentary, they couldn't tune away from each other. They effectively jammed the rescue ships. The emergency responders couldn't get official survivor lists through to the shore because the public was screaming too loud without a standard. Before 1912, radio was a luxury, something military and naval leaders used only when it was convenient. But the fact that a ship 10 miles away didn't hear a single cry because the operator was asleep changed the world forever. The lesson was brutal. Intelligence is a 24/7, 365 business. This was the death of optional radio and the birth of the mandatory watch floor. On a modern warship, the radio eye never blinks. The operators don't get to go to bed. If the ship is at sea, the spectrum is being watched. Period. But watching the airwaves isn't enough. You have to know what matters. The Titanic's operator ignored the ice warning because he was busy sending personal telegrams for wealthy passengers. He treated intelligence like spam because it didn't have a label. Today, we have the priority of signal. Every military transmission has a hierarchy. If an emergency signal or a target lock is detected, the computer automatically bumps routine traffic off the airwaves. We have learned that data is useless unless the most important signal is always at the top of the stack. This tragedy forced the US Navy into a new kind of mission, the International Ice Patrol. This was the first time we used the mathematical ghost for a persistent global intelligence mission. We moved from reacting to threats to predicting them, the birth of global maritime awareness. By creating a shared, real-time map of the environment, the military proved that the ghost could be more than just a messenger. It could be a sentry that keeps the entire world safe from the unseen. To this day, the personnel of the International Ice Patrol carry on a somber tradition. On their first reconnaissance flight each season, they drop a memorial wreath over the exact site where the Titanic rests. A silent tribute to the lives that gave birth to their mission. It is a reminder that in the world of intelligence, we don't just watch the spectrum to win wars. We watch it to protect the living. I'm Keith Sanks, and thank you for watching this episode of The Science of Military Intelligence. Information is the only weapon that never misses. We'll see you in the next one.